Chapter 5, Torsion, Part A, Formula Derivation. If we do have a solid cylindrical shaft with the length of L, happen to handle a torsional torque of T applied at free end, and we want to observe the uh, change in elements. So there is a rotational angle here. We know that that's a shearing strain introduced by gamma, and at the same time we define a another angle called goes by phi, and the radius, the undeveloped radius r here, it's called that rho. We'll get back to it. Mhm. So if we want to observe the length of this arc, which both these angles facing the same arc, so L times gamma, length times gamma, angle of gamma is equal to rho times angle of phi, because they both facing to the same arc. So and if we want to have gamma from that, gamma is nothing but rho phi over L. Mhm. From On the other side, from Hooke's law in shear, we do know that tau is g times gamma, and also tau maximum is a rigidity modulus times gamma maximum. Mhm. So we can just replace the gamma from here into our formula for tau. So tau is g times gamma. Replace gamma from the relation from geometry. So tau is g times rho phi over L. And likewise, tau maximum goes by the, just consider that's a partial of our shaft. And if it just goes by the total radius r, or total radius c, so that goes by tau maximum. Mhm. So in that terms, rho is changing from 0 to c. That's why we call that undeveloped r. So the relation of, and if we just we call this equation 1, mhm, and that's our first equation for torsion. Tau maximum is g rigidity modulus times radius times phi over L. And if we just divide these two equations, we can get the equation of tau based on tau maximum, and that's the ratio of rho over c, or rho undeveloped r to the uh, whole radius r times tau maximum. From the At the other hand, we know a torsion is integration of rho times tau times dA. And how is that? A torsional torque is equal to an arm. Any moment is an arm times force. So torsional torque is in the nature of a moment. So any moment is an arm times a force, which rho stands for our arm, and tau dA, which is the shear times the element, it giving us the force. So, and if we write the equation based on the equation which we just calculate in previous slides. So what's that? How it's is rho c, the ratio of undeveloped r to whole radius times tau maximum, and that's our tau. And we replace that with the previous equation, and if we just take the constant out of the integration, so take tau maximum and c, which are constant, out of integration, So T torsional torque is equal to tau maximum over C times integration of rho squared dA. And that's a interesting fact which gives us, if we do have an element, let's have it here. If we do have an element in X, and if we just want to calculate Ix, it's y squared dA, Iy is x squared dA, and IO is equal to x squared plus y squared dA, and that's IO is r squared dA. And Ix is moment of inertia about x-axis, Iy is moment of inertia about y-axis, and Io is a polar moment of inertia. So we do have rho squared dA, so that's our polar moment of inertia. So that's our polar moment of inertia. So if we replace this term with polar moment of inertia and rewrite our equation, we get T torsion is tau maximum over C times J. And if we arrange our equation based on tau maximum, it gives us tau maximum is equal to torsional torque times C over polar moment of inertia. And if we call this equation 2, just have equation 1 from previous slide part and equation 2 from here, and just by having these two equations, one of them is based on our geometry, which we calculate based on gamma, and phi gives us tau maximum is G times C times phi over L, and the other based on the integration of force times area, force times area times arm, which gives us tau maximum. It gives us the torsional torque. So if both of them are tau maximum, they are equal to each other. If one is equal to 2, then cancel out C from both of equations and rearrange the equation, rewrite it based on phi. It gives us phi is TL times GJ. And that's a very interesting result that says if you have a torsional, if you have a solid cylinder fixed at A and free at B, happen to handle a torsional torque of T, the angle of phi, angle of twist or angle of torsion, it's nothing but torsion times length of the shaft over rigidity modulus time polar moment of inertia. If you remember, if we do have a cantilever beam handling an axial force of F or N, in that case delta was N times L over EA. So you can see how these two equations are identical to each other in their appropriated force. This is delta deformation in axial force condition. This is angle of torsion when you happen to handle a torsional torque. In general, phi, like delta in uh, axial load, goes by two main category of first discrete shape or separated parts and continuous shape. So first one is when you have a different diameter, different shaft with different, for example, solid or hollow shaft with different material, different diameters, happen to handle different uh, torsional torque. And in that case, phi is summation of Ti times Li over Gi Ji from I to n for any number of different block that you have. And in continuous shape, you have no way but an integration from 0 to L of what? Tx dx over gjx. And that's when you have a shape which is changing in cross-sectional area, either linearly or non-linearly.